Hey, welcome back, Physics 30. So I left you with two questions to do here, looking at these two vectors. So if we look at the first one here, scale 1 centimeter equals, okay, so I wouldn't make 1 equals 1 because I'd have to draw it 32 meters. If I made it 2, let's see, 2 times 16, that's a little big. Even 3 is a little big, but 32 is also divisible by 8. So that might work, because if I wanted to make something that's 32 meters, that of course is times 4, hey, and times 4, so 4 centimeters would represent 32. So if 1 is 8, then 4 is 32. Now also if I'm looking here, again with the direction convention, north, east, southwest, northwest. So again, this is where my 0, this is where I start. So north, and then I'm going in the west direction. So this is a quadrant 2 vector. So it wouldn't make sense to start over here because I'll be going off the page. I'll likely start somewhere over here. And then right there I'll make my little Cartesian coordinate system. So my horizontal line. And then you can sneakily make the perpendicular line. If you take one of the lines on the rulers and line it up, you'll automatically have a 90-degree angle there, and we have our quadrant 1, 2, 3, 4. So north, then go west. So north, so obviously I wouldn't put so here's a 0 scale, and it'd be good if I was going east, but I want to go west. So I orientate my protractor like this, and I'm going west. So 0, 10, 20, 30. I'm going to end up going through my scale a little bit, but that's okay. So there's my dot right over there. And I'm going to make this 4 centimeters. So let's see, if I put this at 10, so if I put it at the 10 mark, let's see here. So 1, 2, 3, oh, I'm going to be going into my scale, darn it. That's all right. And then put my arrowhead there, so that's 4 centimeters if I measure it. 4 centimeters is 32, and of course this was the angle here that I figured out to be 33 degrees, so I'll just mark that, and that is V3. Alright, so looking at the next one, again I'm going to make a scale. 1 centimeter equals so many meters. Now this is a fairly big number. It's divisible by 5, but still that'll be a very big number. But 25 goes into that. So if 1 equals 25, then to draw 125, 25, 50, 75, 100, 125, that would be 5 centimeters. So times 5, times 5. So if I draw it 5 centimeters, that'll work. And of course, in this case, I'm starting off west and moving south. So starting west, moving south, that's a quadrant 3 vector. So it'll be pointing in this direction, so it's likely a good idea to maybe start over here somewhere with my starting point in my little Cartesian coordinate system that I'm going to make up. So go like that. And again, put your ruler so that your line is overlapping this line. And then I automatically have a 90-degree angle, and you can see my quadrants, 1, 2, 3, 4. So from west, go south. So from west, go south, and I'm going 15 degrees. So let's see here, 0, here's my 10, here's my 20, so 15 we can see is midway in between. So right there. And yes, I want to make this 5 centimeters. So let's see, if I put my 10 right here, I'm going to go 1, 2, 3, 4, 5. So right here is my tip right there. So draw your line, and you can see my tip is right there. I kind of went a little bit long with my marker, but the tip of the arrow represents where the vector ends. So you can see that's 5 centimeters. And of course, this is the angle that we measured, 15. So that is vector V4. Alright, so that's how you draw vectors using a scale diagram, using a ruler and protractor. And of course, You may or may not have a lot of experience using a protractor, but of course there's the two scales there, 0 to 180 or 0 to 180, which makes it handy when going in these particular map directions right here. So now we know how to draw vectors and what they look like. Let's look at adding vectors. Now there are different types of scenarios that we could look at, but we'll start with the easiest one, looking at linear vectors. So for vectors in one dimension, simple addition and subtraction are all that are needed if they are linear, i.e. they're on the same line. So if we look at this first one, and be careful with signs here too. So if I look at this, just draw that direction convention again. So I have north, east, south, west. And of course the east-west line is really the positive x and negative x line. And the north-south is the positive y and negative y line. Because that's what we can use here. So for math class, you know that positive x, positive y, negative y. And using map notation, northeast, southwest. So if we're adding two vectors 8 kilometers east, then from there go a further 6 kilometers east. We're looking at adding the two vectors. It's easy when they're linear like this, because we just simply can draw them out. So we have 8 kilometers east, and to that add another 6 kilometers. So if we started here, we finish here, the resultant vector is always from start to finish directly. We're not concerned about how we got there. We're just simply looking at it from start to finish. So from here to here, so of course 8 kilometers east is the same thing as positive 8 on the x-axis. 6 kilometers east is the same thing as positive 6 on the x-axis. So plus 8 and plus 6 is plus 14. And of course plus on the x-axis represents east. All right. If you look at this one, going 8 kilometers east, then 6 kilometers west. So if I'm starting here, 8 kilometers east, then from there goes 6 kilometers west. So I'm going to finish right there. So going from start to finish, we can see is this little section here, which of course is 2. If we look at it mathematically, 8 kilometers east is the same thing as plus 8. 6 kilometers west is the same thing as negative 6 on this x number line. So of course adding that, we get positive 2. And of course positive on the x-axis means east. So again, the resultant vector is simply your movement from start to finish when all is said and done. So if the motion is in 2 dimensions, the situation is a little more difficult. So if they're on the same line, whether it's the x-axis or the y-axis, plus, minus, it's just simply adding them together. One key thing to note here is that we're adding a negative. So we don't usually call it subtraction. We refer to it as adding a negative. So on the next page, what if if I have two vectors and they form a right triangle? So as seen on the right, the actual travel paths are at right angles to each other. The displacement can be determined. Yes, we have the old c squared equals a squared plus b squared, or c is equal to the square root of a squared plus b squared. So that's where this comes from. If I'm talking about displacement or some other vector, or I could call it v, it's side squared plus side squared. So d1 squared plus d2 squared gives me resultant vector squared. Now usually when we talk about vector addition, no matter what, we just simply refer to it as, okay, the resultant vector is equal to the first vector plus the second vector. But we just simply can't take 10 plus 4 because they're not linear. That works for the linear case where they're on the same line, but of course it doesn't work for right angled type triangles. So if we went 10 kilometers per east, then 4 kilometers north, vector addition, meaning that in reality I'm going to have to use the rules for right triangles. So 10 squared plus 4 squared, and take the square root of that, I get 11. So this is going to be 11 kilometers. And of course I need to know what this direction is. Now over here I know the opposite side. So D2 represents the opposite side, and D1 represents the adjacent side. And I know the hypotenuse here as well because I did that calculation. But it's best to use numbers that are given to you in the question. So opposite over adjacent, that of course is 10. So 4 over 10. So the tan of whatever theta that is, whatever angle is going to be 0.4. But of course, I want to do the inverse operation. To know what angle it is, I have to take the inverse tan of 0.4, and I get 21.8. So this is 21.8. And I, of course, know that this vector is pointing in quad 1. So I'm either going to state in terms of east so many degrees north or north so many degrees east. And as you can see here, because I have a vector already drawn east, it's likely easier to do this. Plus, of course, when I was finding out tan, I was using this triangle. My opposite side was here, and my adjacent side was here. So I'm stuck with stating the direction in terms of east, so many degrees north. So that's what we have right here. East, 21.8 degrees north, and of course that's 11 kilometers per hour. Now, so I originally drew it as D1 plus D2, but of course I could have drawn it as D2 plus D1 as illustrated down here. My opposite and my adjacent side are slightly different, and in that case I would be looking at this angle. So in other words, 90 minus 21.8, which is 68.2. But adding them up, I would get the same result. It'd work out to be 11 kilometers, and in this case, north 68.2 degrees east. All right. So on the next page, we have an example that we're going to be looking at. So maybe I'll get you to try that example and then come and look at the next video to see how you did. All right, we'll see you again.